We'll start now. We were discussing about the Neyman Pearson technique, right? So it is the type of deduction technique. What we discussed was Bayes technique. That is the best choice for the deduction, which is followed by Minimax technique. When the prior probability is not known, then we go for this Minimax technique. The third choice is the Neyman Pearson technique. That is what we are going to do. Neyman Pearson technique involves this optimization problem. It is like we would like to maximize this probability of detection with the constraint this probability of false alarm to be less than or equal to some constant alpha, which is basically the size of the problem. Right? The solution to this Neyman Pearson technique, particularly for the binary channel model, involves this randomized decision rule. Randomized decision rule of the form like this. We have 4 cases in that. 1 0, y equal to 1, and then y, I mean 1 gamma, I'm sorry. And delta of y equal to 1 gamma 0, y equal to 1 here, and we have delta of y gamma 0, y equal to 1, y equal to 0. Delta of y is gamma 0, y equal to 1. So what I'm trying to say here is the Neyman Pearson solution ends up with randomized decision rule, like what I have mentioned in the list. Particularly for the binary channel model, it takes any of these 4 combinations, 3 or 4 combinations, such that probability of false alarm is exactly equal to alpha. That is what I would like to convey. Our interest is probability of false alarm to be less than alpha, less than or equal to alpha. It is not possible to reduce this probability of false alarm beyond this value alpha. So I mean, to maximize this probability of detection, the restriction for this probability of false alarm is to equate this probability of false alarm exactly equal to alpha. This probability of false alarm equal to alpha, and then you have to find out which rule among these 4, which among these 4 is going to have a maximum probability of detection, that we will declare it as a solution. We'll do one problem now. Let us consider the binary channel model with the characteristics. One given 0 is 0.6. Probability of 0 given 1 is 0.2. Right? So now for the individual case 1, case 2, case 3, and case 4, we'll calculate what is that probability of false alarm and then probability of detection, which we discussed in the previous class. Today with the value we are going to use. class we had the expression here. Last class we did that. So this time now we are having values for this. Probability of y equal to 0 given 1 and all, right? So we have 4 rules, right? Just recollect what we discussed in the previous class. For rule 1, we have the expression false alarm and as well as probability of detection. It is there in your notebook. Anyhow, we'll do it again. We have to compute this probability of false alarm now, but with the values are now known. This is what the value of y, I mean the probability that y equal to 1 when 0 is transmitted, right? So this is that transition probability of the channel. So what we are considering is binary channel model. So it is like 0 1 0 1 and probability 0, right? So this is 0.6 and this is going to be your 0.2 here, right? So other things are obvious, right? Because when you add row wise the channel matrix end up with 1, right? So probability of 0 given 0 is going to be 0.4, right? So condition on same thing, probability of 0 given 0, that is going to be your 0.4, and condition on 1, that is probability of 1 given 1, so that is going to be your 0.8, right? So these things we already know, right? So this is the characteristics of this binary channel model. We'll write it again. Probability of 0 given 0 is 0.4 and probability of 1 given 1 is 0.8. Now I want you to compute this probability of false alarm for the first case here, right? So and I already told, once again I recollect, these values are probabilities, and delta of y is basically the randomized decision rule, always deciding in favor of one with a different probability. When you receive y equal to 1, you decide that x is equal to 1 with probability 1, and when you receive y equal to 0, you decide in favor of 1. That is what is being transmitted from the transmitter is 1 with gamma. So what is being transmitted from the transmitter, you have to assume that it is 0. You have to declare that it is 0 with probability 1 minus gamma. So gamma is the probability, 1 is the probability, right? So this is already know. So what is probability of false alarm? Probability of false alarm is basically when you say the target is present when actually the target is not there. So it is related with the case when x is equal to 0, when x is 0, right? When target is absent. So that probability is what actually we have to use it here, right? So to get a false alarm, you are getting false alarm in both the case, when you are getting equal to 1 as well as y equal to 0. In both the case you are getting that false alarm, 0 is transmitted. That means when you are getting y equal to, when 0 is transmitted, as well as when we are getting y equal to 0 when 0 is transmitted. In both the case you are actually getting the probability of false alarm, but you have other probabilities also involved in it, right? So that means when and you are getting y equal to 1, that alone is not enough, and you have to declare that it is 1. So the probability that you declare that it is 1 is 1 here. So this is multiplied with 1 in this, and similarly here you declare them, right? When you are receiving y equal to 0, you are transmitted from the transmitter as 1 is probability gamma. So this is multiplied with gamma, and this is going to be your probability of false alarm. And now let us do this task. Let us consider this problem that is equal to, alpha value. We'll choose this alpha value as 0.1. To do this task, basically the size of the problem, right? So that alpha is coming. This is the location where this probability of false alarm is what? Less than or equal to alpha, right? So you are fixing this alpha equal to 0.1, right? So now we need to compute this. Probability of y equal to 1 given 0, which is 0.6 here, plus probability of 0 given 0, which is 0.4 here, 0.4 gamma, and this one to 0.1, right? And then you need to solve for, right? So what is that value of gamma you are getting in this case? Yes. Someone type the answer on the chat window. What is the value of gamma? Minus, right? It is coming as minus, and that too, it is greater than 1 also. It is negative, first of all. It is not at all a valid probability. Gamma is basically the probability. So when you are getting negative, this case is not going to occur, right? We are not going to use this case for this Neyman Pearson. So we will go for the second case now, case 2. Case 2, the same procedure. We have to go for this calculation of this probability of false alarm. So this is the rule, second rule, right? So this is basically probability of 0 when 0 is transmitted into 1, right? Plus probability of y equal to 1 when 0 gamma, right? So this is what we say that it is probability of false alarm 0.1. So what is the value of gamma now? Probability of y equal to 0 given 0, it is 0.4 in this, 0.4 plus 1 given 0. Correct me if I'm doing some mistakes. So probability of y equal to 1 given 0, which is 0.6 here. That is equal to what? 0.1 here, right? In this case also, gamma is going to be the negative. Gamma is negative. It is not. We have to go for case 3. Is this? This is the case 3 here. So we'll go for this probability of false alarm calculation now, which is equal to y equal to 1 when 0 is transmitted into gamma now, because this probability is gamma, plus probability of y equal to 0 is transmitted into 0 here. So this is equal to 0.1. The probability of y equal to 1 is 0.6 in this. So this is 0.6 gamma. That is equal to, this is anyhow, it is going to be 0, second part, equal to 0.1. Gamma is 1 by 6. Fine. This is a valid equation, but we cannot declare immediately case 3 as a Neyman Pearson solution for this case. For this particular problem. We will go for case 4 also. Case 4, probability of false. Case 4, right? So which is basically probability of y equal to 0 when 0 is transmitted into gamma, probability of y equal to 1 given 0 into 0, that is equal to 0.1 here, and the probability of y equal to 0, which is 0.4 in this case. So 0.4 gamma plus 0 equal to 0.1. Then we can actually find the gamma value as 1 by 4, right? So both are valid actually. Case 3 and case 4 both are valid, but we have to choose one. How do we choose? Among 3 and 4, one rule we are going to freeze because case 1 and case 2 they are ruled out. Among this case 3 and case 4 we have to choose one among them, right? Our goal is actually to minimize the probability of deduction, right? So for case 1 and case 2 we need not find out probability of deduction because already this gamma is negative, so we need not do that. But when it comes to this case 3 and case 4, we can actually calculate this probability of deduction. I want you to calculate and write the answer for probability of deduction case 3, what is the value, and for case 4 the same method you can follow and tell me what is the value of this probability of deduction. Only thing is you are having the same expression, only thing is you have to go for when 1 is transmitted, right? So that is the only difference. So I give some time for you to calculate. So you tell me the answer now. So what is the expression for the probability of deduction? Probability of y equal to 1. I mean, when 1 is transmitted, the difference. That is the change here. And probability of y equal to 0 when 1 is transmitted into 0 here, right? Right. So anyhow, the second term is going to be 0 in this. What is that probability of y equal to 1 given 1? Which is 0.8 here. So 0.8 into gamma. For case 3, we already got that gamma value as 1 by 6. So into 1 by 6 will come. So this is going at case 3 probability of deduction. Simplify and tell me for case 4 the same fashion. Probability of deduction. So that is probability of y equal to 0 when 1 is transmitted into gamma plus probability of y equal to 1 when 1 is transmitted into 0 here, right? So anyhow that second term is going to be 0 in this. Probability of y equal to 0 given 1, which is 0.2 in this problem, right? So this is 0.2. So 0.2 into gamma is 1 by 4 for case 4 So this is the value. You have to see whichever is greater among these two. In this case, whichever is greater actually. So this is coming as what? So tell me which is greater here? Case 3, right? So we have to declare finally. Declare the Neyman-Pearson rule for the given binary channel model as delta of y. This is a rule now, right? So we are going to declare that rule as this 0.13 and this is 0.05. Okay, so we have to fix whichever is greater. So case 3 only we have to fix now. Case 3, the like this. Case 3, this is the rule here. So we have to write that rule: gamma y equal to 1, 0 y equal to 0. Right? But we know the value of gamma case 3. Case 3, the value of gamma is 1 by 6. We can still rewrite this as 1 by 6 here. This is the Neyman-Pearson rule, what we identified. This is the rule, deduction rule, right? Neyman-Pearson deduction rule for the given scenario. Given scenario means you are given a probability of 1 given 0, 6. This is the binary channel model, right? What is given to you? Probability of 0 given 1, which is 0.2 here. For this particular combination, the final rule obtained, the Neyman-Pearson rule is like this, right? This will help that probability of false alarm to be less than or equal to the size of the problem is already given, that is for this particular problem it is 0.1, less than or equal to 0.1. In fact, false alarm equated to 0.1. Our objective is to get less than 0.1, but solution, right, will end up probability of false alarm is exactly equal to 0.1, because if I still reduce this probability of false alarm, the probability of detection will come down. Now we got this probability of detection is 0.13, very less, but it will come down if you have this probability of false alarm, right? Still less than this 0.1. So that is the trade-off, right? Can you repeat this for probability of false alarm that is equal to probability of false alarm alpha value? You repeat this problem for alpha equal to 0.01. And quickly, I'll give you time, 2 minutes time. Right, so this is the Neyman-Pearson solution, generalized, which is of randomized decision rule. This is more general, not for restricting to this binary channel model. You see here, in case of binary channel model, this is the region, right? We we view this as a three different regions, non-overlapping region, right? This is the region 1, This is region 2. This is region 3. They are disjoint and your beta value is positive, right? And these are all the probabilities. 1, u of y and 0, they are all the probabilities, right? So as you know, this is that randomized decision rule. What you get here is the probability only. The specific for the binary channel model, region 1, right? So I can compare like 1. So this is equal to y equal to 1 here. And in place of u of y, it is given as gamma equal to 0. So that is the one special case, right? Among the 4 cases what we had it for the binary channel model. The second case, in this case, we have this y equal to 1 and y equal to 0. They are all the region, set of values of y. In case of binary channel model, we had only 2 values, y equal to 1 and y equal to 0. That is the reason we have written directly the expression like that. But Neyman-Pearson solution is meant for the continuous case also. So basically what is given here, right, this box, right? So the circle what I have circled here, this is basically the region. We can say that it is a region, set of values for y, right? That satisfies this condition with beta as positive. Set of all values of y such that probability of y given 1 is greater than beta times probability of y given 0, right? So that is the region 1. And set of all values of y such that probability of y given 1 is equal to beta times probability of y given 0, that is region 2. And probability of y equal to 1 less than beta times probability of y given 0, that is region 3. So these are all the 3 different regions, region 1, region 2, region 3. For every region, we have a corresponding probability associated with that. All are in favor of 1, right? I mean, deciding what is being transmitted from the transmitter is 1, in favor of 1. Just like this is an example, what we had is the example for the binary channel model, and this is more general expression for the Neyman-Pearson technique. You must know the general expression also, right? So as far as this Neyman-Pearson solution is considered, so the solution, now let me put the Neyman-Pearson statement like this. The problem is you wanted that probability of false alarm to be less than or equal to alpha. Alpha is basically the size of the problem, and you wanted this probability of detection to be maximized. So that is the goal. That is the optimization problem structured for the Neyman-Pearson case. And this alpha is what we call it as the size of the problem. The solution, the Neyman-Pearson solution, follows the randomized decision rule of this form, what I have written here, right? Delta of y equal to 1 if probability of y given 1 greater than beta times probability of y given 0, and that is equal to u of y, it is a function of y, if probability of y given 1 is equal to beta times probability of y given 0, and delta of y equal to 0 if probability of y given 1 is less than beta times probability of y given 0. And once again I remind you, these are the probabilities. As far as randomized decision rule is considered, this is the probability. And as usual, it takes of this form randomized decision rule such that the probability of false alarm is exactly equal to what? Alpha. We cannot actually get a solution that gives you the probability of false alarm less than alpha. If I try to reduce this probability of false alarm, then you will not get probability of detection to be greater. So we have to restrict the probability of false alarm exactly equal to alpha, and for that only we get a solution. which is of the randomized decision rule, right? And this is about this Neyman Pearson technique. We have some characteristics for this Neyman Pearson technique that we will discuss in the coming class, right? So there are three important observations what we can do with Neyman Pearson technique. One is the uniqueness of the solution, right? The existence and optimality, right? All those things we are going to discuss. First of all, whether the solution exists in under all circumstances, right? So we have some characteristics. So those things we will discuss in the coming class. What I want to convey is the name and solution is the randomized decision rule of the form what is shown on the slide. So this is very important. Beta is the positive quantity. That is very important because in the coming class we are going to discuss about the characteristics of this Neyman Pearson technique. More general, right? What we if the problem is a specific case where we had the binary channel model, but you can have the Neyman Pearson technique more general case also. Even a simple additive Gaussian noise model also we can actually use this Neyman Pearson technique, right? So in the coming class we are going to discuss about the characteristics of the Neyman Pearson technique, and then followed by whatever we discussed so far, the Bayes technique, Minimax technique and Neyman Pearson technique, everything we restricted ourselves to the binary channel model. So we will do the same Bayes, Minimax and Neyman Pearson technique for additive Gaussian noise model also. In the coming class we are going to do all those things, right? We will stop here and we'll wind up now. Bye.